Hello Philippines, hello world, welcome again to my YT channel. I am a singer, eternal voice. So we need to continue problem number 6. Okay, so this is all about problem solving with the application of science formulas. So if you are having upcoming examinations, for example, board examination, specifically engineering board examination, then you can stand by for a while and listen to this short vlog regarding problem solving computation. So now we are doing the work and energy, problem solving. Okay, number 6. An 8-kilogram block compresses a horizontal spring with a constant equal to 300 Newton per meter by 2.5 meter beyond its natural length. Okay, like that. So, A, what is the speed of the block as it released from spring? B, how high up the hill will the block go? Okay, so again, let's use the conservation of energy, which is mechanical energy at point 1 is equal to mechanical energy at point 2. Since this is a spring, so we need to use the formula of the spring from the Hooke's law, right? We need to use the elasticity potential energy that is equal to 1/2 times the constant key times the distance covered during the stretching of the spring, something like that. X raised to the power 2, so 1/2. Okay, key x raised to the power 2. X is the distance covered when you stretch the spring, something like that. And the spring will like this and bounce back like this. Okay, so we need to show the illustration now. Okay. This is gonna be like this. Okay, so we have here the spring. Okay, this is the spring. And this is the black 8 kilogram. Okay, like this. Like this. This is the illustration. We have the block of 8 kilogram and there's a spring and we need to compress that one like this. And after compression, it will move this block, and let's have an imagination that the block will be going here. Okay, so it has covered a distance of 2.5 meter. So it's in here that you will apply the Hooke's law. Okay, and then after that, from point here to here, it will go to a cliff like this, and there's a height from here to here. Okay, we need to compute later for this height if this block reaches here, something like that. Okay, and then we use the formula mechanical energy at point, let's say A, B, and C. See, this is point A, B, and C. Okay, so we need to cut this one first. We need to focus first for A and B, and then later for B and C. Or it's up to you if you need the total energies and then solve for what is being required and input the given directly. You can also use that one, but for me it's better to cut off so that we can easily solve what is being required. So this one is gonna be mechanical energy 1 is equals to mechanical energy 2, or A, B, and mechanical energy C. Mechanical energy A, mechanical energy B, mechanical energy C. So later we will compute this mechanical energy C, but we just focus in these two. Mechanical energy A is equals to mechanical energy B. So mechanical energy A, we have potential energy, right? So potential energy, which is mass times g times height supposedly, but in here we are dealing with the Hooke's law of spring. Is okay, so elasticity potential energy we will use here. Okay, so elasticity potential energy, the formula is not mgh, it is 1/2, like this, 1/2 key x squared. Okay, so elasticity energy formula, and then we have the potential energy, but the potential energy is not used here, huh? Okay, so that's it. So this is the elasticity kinetic energy pala siya, because that is elasticity man siya, so there's a movement, sorry. Okay, like that. Okay, so since our 8 kilogram block here, so it's not covering a height yet, h, so this is 0, so our potential energy will be 0, right, or cancelled. So this one will be used now as our elastic or elasticity kinetic energy, right? 1/2 kx squared, or the formula of the spring. This is for the movement, right, in parallel of the 1/2 mv squared. Okay, like that. Since this is a spring, we will never use the 1/2 mv squared. Instead, we will use the 1/2, okay, times k times x raised to the power 2. Okay, now equal to the, okay, mechanical energy B, kinetic energy plus potential energy again. Okay, like that. So in here we don't have the height also, so we need to put 0 for the potential energy. So this is 1/2 mv squared. Okay, like that. Okay, so 1/2 kx squared is equals to 1/2 mv squared. This is the spring formula of the elasticity kinetic energy. Okay, and this is the at point B kinetic energy moving with the velocity. So we need to substitute values now. Okay, our k is given in the problem, which is k is equals to weight plus k is 300 Newton meter. Required A is the speed of the block. The speed of the block, or the speed, so speed V, so speed of the block only, so it doesn't concern with the direction, only the magnitude. And the negative and positive sign is not really that relevant here. Okay, because speed is a scalar quantity. Okay, so we treat here velocity here pala is a speed, not the velocity vector. Okay, like this. So 1/2 k 300. Okay, and the x guys here, the x is this distance covered by during the action of the compression of the spring to this block. It is 2.5 meter. Substitute that here. Okay, so 2.5 meter raised to the power 2. is equals to 1/2. There's the mass of the black, and then you can solve for the velocity. It's here, or the speed. You can solve the speed directly, very easy, right? So the speed is, okay, the mathematical operation, so 2.5 squared. Okay, so times 300. Okay, 2.5 times 2.5 is equals to 625 times 150. So 97.5 divided by 4, right? Square root. So the speed is 21.6 meter per second. So this is our speed. So the speed is 21.6 meter per second in attaining this imaginary second block, as it will move here during the compression originally of this block here for the spring. Okay, 21.6. Now this is the answer for letter A. What is the speed of the block as it released from the spring? So 21.6 meter per second. Now we need to equate the mechanical energy B to mechanical energy C. We are done here, the first part. So we equate that one. So mechanical energy B is equals to mechanical energy C. Okay. Mechanical energy B is the point in which the block is being compressed and moved by the spring, and then this C will be the position of the block as it reaches to the cliff or hill here, like this. Okay. Because it will suddenly, like that, very strong impact will go to the cliff. Okay, so let's analyze that during that situation. So mechanical energy B, so potential energy, always like the top, potential energy plus kinetic energy plus the fraction. But in here, we don't have fraction that acted in the surface. So we treat the fraction acted in the surface as 0. Okay, or the energy due to fraction. It's not here. It's not present, and it's not being mentioned on the problem also. So potential energy B is equals to kinetic energy B is equals to potential energy C plus kinetic energy C. So let's analyze number 1. In the point B, okay, so in the point B, we don't have the height covered in B because it's still in the horizontal. And the formula of potential energy class is mgho man siya. If we substitute 0 heights, it will become 0. So potential energy will be 0. Okay? Like that. Okay? And in here also, the Hawk's law and of the spring is no longer applicable because the compression has been done already. It moved to a distance naman talaga and a velocity of 21. Speed of 21.6 meter per second. Okay, and then there's a kinetic energy, of course, when it reached to B. Okay, so in the C we have the potential energy. Yes, we have the potential energy because it reaches to a cliff like this, cliff from 0 to height above, which is the height we need to compute. So there's a potential energy of this block after going to the cliff. So since in going to the cliff class, the block will stop. The block will stop in going to the cliff, so there's no kinetic energy there anymore because the block will stop. Okay, so kinetic energy will be cancelled, only the potential energy. So in short, only this remain. So MA at point B is equals to kinetic energy in point B is equals to the mechanical energy, okay, here. So the kinetic energy is cancelled because it has been stopped in the cliff. So there's no potential energy. So kinetic energy at C na lang siya. So substitute the formulas, individual formulas. Kinetic energy at point B, 1/2 mv squared. So the V we computed already, 21.6 raised to the power 2. Okay, like that. Okay, the potential energy and GH, like this. Okay. Okay, like that. Okay, it's very clear. So MGH. Actually, we need to consider also the triangle here. Okay, triangle, but this is a curve, not the inclined plane straight line. So, and the angle is not also given in the problem. So we cannot assume that there is a angle inclination value. This is curve, okay? So it's not really that straight, you know, inclined surface. So we cannot assume that there's an angle of inclination. So we will not consider the angle of inclination in this here, in the height computation. We don't use a sine theta, cosine theta like that, okay? Direct na siya. So 1/2 times 6, the mass, okay, is 8 kilogram. Velocity 21.6 raised to the power 2 is equals to 8. Gravity 9.81 times h, and h like this will be solved. H will be solved directly through substituting values. Okay? Okay, class? Again, we don't consider the angle of inclination here. From here to here, we don't. Actually, there's an angle of inclination, and we need to use the sin theta again, like this from the Pythagorean theorem. We don't use that one because it was not mentioned in the problem that there's an angle. It's the first thing. Number 2, this is really a curve. We don't know exactly if it is a straight diagonal hypotenuse. It will not produce a straight diagonal hypotenuse man siya. Okay, for that reasons, we don't incorporate the angle. Okay, for the h, like this. So the height is simply like this. So 21.6 times 21, okay, 21.6, 21.6 squared times 4. So 1866.24, and then, sorry, reverse, 1866.24, then 9.81 times 8, 78.48, then 1866.24 divided by 78.48. Okay, so the height is 23.8 meters. This is the height. So this is the height at point C in which the black will reach at the top of the hill. Okay, 23.8 meters here. So like this. So this is the 23.8 meter height as this block which is there at the top. So we solve already here. 23.8 meters the height with the block which is at this cliff after the, you know, the principle of Hooke's law, compression through the spring here originally at point 1. So we have the velocity 21.6. Okay, so for A, what is the speed of the block as it released from the spring? We have 21.6 meters per second. And how high up the hill will the block go? So 23.8 meters. Okay, thank you so much for watching this short vlog of mine regarding conservation of energies, the mechanical energies at certain point, and then you have to incorporate the summation of all energies, specifically the potential energy, the kinetic energy. If we have the frictional energy also, wasted energy due to the fraction, then you can add that also there and consider the movement of the fraction that's always opposing from the movement, okay, of the original block or whatever. It's always opposed from the applied force, something like that, or for the motion of the particular object that is undergoing a motion or a movement. Okay, so speed, the direction is not necessary, or the sign, negative or positive, but for the velocity, sign negative and positive is very important because it indicates whether it has a reduced speed or increasing speed, or shall consider the direction of the certain objects, how far that it moves, like this, point A, point B, point C, point D. So it's gonna be like that, okay? So, conservation of energies, okay? Thank you so much for watching this vlog. If you are not subscribing yet my YT channel, then you can subscribe now and click for some notification bell for newest updates. I'm seeing it in our voice notification bell. Thank you so much. Bye bye, God bless everybody.